The perfect storm ingredients? Tornadoes don't appear out of nowhere. They need just the right combination of atmospheric ingredients, much like a recipe. The first key ingredient is warm, moist air near the surface, usually carried northward from the Gulf of Mexico in the United States. This air is light and tends to rise quickly. The second ingredient is cool, dry air above, often coming down from the Rocky Mountains or from Canada. When these two very different air masses meet, the atmosphere becomes unstable, which means the warm air near the surface wants to rise rapidly. A third crucial ingredient is wind shear, which refers to changes in wind speed or direction at different heights. Near the ground, winds may blow slowly from the south, while several thousand feet up, winds may rush much faster from the west. This difference creates horizontal tubes of rotating air. These three ingredients, instability, moisture, and wind shear, create the environment in which powerful thunderstorms and eventually tornadoes can develop. Without all three working together, the odds of a tornado forming drop dramatically. Thunderstorms take shape. The first visible step toward a tornado is the formation of a thunderstorm. When the warm, moist air at the surface rises, it cools as it goes higher into the atmosphere. Cooler air cannot hold as much moisture, so the water vapor condenses into tiny droplets, forming clouds. As the condensation happens, heat is released. This is called latent heat, and it gives the rising air an extra boost upward. This upward surge of air is called an updraft. Over time, the cloud builds higher and higher until it forms a tall, anvil-shaped cumulonimbus cloud, which is the hallmark of strong thunderstorms. If the updraft is especially powerful and the atmosphere is unstable enough, the storm can develop into a supercell thunderstorm. Supercells are rare, but are the primary type of storm that can spawn tornadoes. The role of wind shear. Wind shear plays a critical role in turning a regular thunderstorm into one capable of producing a tornado. When winds near the ground blow slowly in one direction, but winds a few thousand feet up blow faster and in a slightly different direction, the air begins to roll or rotate horizontally, like an invisible spinning tube. This horizontal rotation is not yet a tornado. It's just spinning air lying flat near the surface. However, when a strong thunderstorm's powerful updraft lifts that spinning tube of air upward, the tube becomes vertical. Once vertical, the rotation can stretch and intensify, forming the seed of what can eventually become a tornado. The stronger the wind shear, the more likely it is that the storm's rotation will be sustained and strengthened. Birth of the mesocyclone. Inside a supercell, the rotating column of air created by the tilted wind shear forms a mesocyclone. A mesocyclone is essentially a large, organized region of rotation inside the thunderstorm itself. It's typically several miles wide and can persist for hours as the supercell moves. Think of it as the storm's rotating engine. It drives the whole process that can lead to a tornado. Not every mesocyclone produces a tornado, but nearly every significant tornado begins within one. Meteorologists often use Doppler radar to detect the presence of mesocyclones because they indicate a higher risk of tornado formation. The downdrafts join in. While the mesocyclone spins inside the storm, another key process happens closer to the ground, the development of downdraft. A downdraft occurs when cooler, heavier air sinks from higher levels of the storm toward the surface. One particularly important downdraft is called the rear flank downdraft. This downdraft wraps around the mesocyclone and helps tighten the rotation. This process is similar to an ice skater pulling in their arms to spin faster. The tightening rotation near the surface increases the chances that a tornado will form. The interaction between the updraft, the mesocyclone, and the rear flank downdraft is one of the final steps in creating a tornado. Funnel cloud formation. As the rotation strengthens near the base of the storm, pressure in the center of the spinning column drops. The lower pressure allows water vapor in the air to condense, creating a visible funnel cloud that extends downward from the base of the storm. At first, the funnel cloud may hang in the air without touching the ground. At this stage, it's not officially a tornado yet. However, the funnel is a visible sign that the rotation is intensifying and stretching toward the surface. If conditions remain favorable, the funnel will continue to grow downward until it makes contact with the ground. Touchdown. A tornado is born. A tornado officially forms when the rotating funnel cloud reaches the ground. Once that connection happens, the column of rotating air begins to draw in debris, dust, and even soil, which often makes the tornado look darker and more menacing. Tornadoes vary widely in size and strength. Some are just a few dozen yards across and last only a few minutes. Others can grow to over a mile wide and stay on the ground for hours, cutting paths of destruction over 50 miles long. The most powerful tornadoes can produce winds exceeding 200 miles per hour, 320 kilometers/h, strong enough to lift cars, strip asphalt from roads, and demolish well-built homes. Energy source and movement. tornado draws its energy from the thunderstorm that spawned it. As long as the storm's updraft continues to pull in warm, moist air from the surface, the tornado can keep spinning. Most tornadoes move in the same direction as the parent storm, often toward the northeast in the United States, at speeds ranging from 10 to 60 miles per hour. If the storm weakens or moves into a region with cooler, drier air, the tornado's energy supply is cut off, and it begins to weaken. Dissipation and the tornado's end. The final stage of a tornado's life is known as the roping out phase. As the energy feeding it diminishes, the tornado narrows into a thin, rope-like column. Even though it looks smaller and less threatening, it can still carry strong winds capable of causing damage. Eventually, the rotation slows down enough that the funnel disappears entirely, and the tornado is over. Some tornadoes last just a few minutes, while others can persist for hours, but they all eventually lose their source of energy. Why some storms don't produce tornadoes? Not all supercell thunderstorms produce tornadoes. Scientists are still studying why some mesocyclones create tornadoes while others do not. Factors such as the exact balance between updrafts and downdrafts, the amount of moisture near the surface, and the pattern of winds all play critical roles. This complexity is why forecasting tornadoes remains one of meteorology's greatest challenges, even with modern technology. The Fujita and enhanced Fujita scales. Once a tornado forms, scientists classify its strength using the Fujita F or enhanced Fujita EF scale. This scale is based on the damage a tornado causes, which correlates with its wind speed. EF0, winds of 65 to 85 mph, damages trees and light structures. EF1, EF2, winds up to 135 miles per hour, can tear roofs from houses and flip vehicles. EF3, EF5, winds over 165 to 200 plus mph, capable of leveling buildings and scouring the ground. This classification helps meteorologists communicate the severity of a tornado and guide emergency response efforts. The role of climate and geography. Geography plays a major role in where tornadoes occur most frequently. In the United States, an area known as Tornado Alley, stretching from Texas up through Oklahoma, Kansas, and Nebraska, sees more tornadoes than almost anywhere else in the world. This is because the flat terrain allows warm, moist air from the Gulf of Mexico to meet cool, dry air from the north and west with few natural barriers, creating ideal conditions for supercells. However, tornadoes can and do occur on every continent except Antarctica. Countries like Bangladesh, Argentina, and South Africa also experience significant tornado activity. Science and safety. Modern science has improved our ability to predict and track tornadoes. Doppler radar, weather satellites, and mobile storm chasers provide real-time data about developing storms. This technology allows meteorologists to issue tornado watches and warnings earlier than in the past, giving people more time to seek shelter. Still, tornadoes can form quickly, sometimes within minutes, making it vital for people in tornado-prone areas to stay alert and have a safety plan.